The algorithmic paradox, balancing speed, memory, and complexity in modern computing. In an era where algorithms power everything from search engines to autonomous vehicles, understanding their efficiency is not merely technical, it's existential. The right choice between a linear scan and a binary search can mean the difference between seconds and years of processing time. This exploration dives deep into the hidden trade-offs that define modern algorithm design, revealing how engineers navigate the treacherous waters of computational complexity while maintaining practical usability. The Big O dilemma, time versus space complexity. At the heart of every algorithm lies a fundamental question: how do we measure efficiency? The answer isn't as simple as counting lines of code or execution speed alone. Big O notation provides a standardized way to describe algorithm performance asymptotically, focusing on growth rates rather than absolute values. This approach reveals critical truths about scalability but often hides implementation nuances. Time complexity measures how execution time grows with input size, while space complexity tracks memory usage. These metrics form the twin pillars of algorithm analysis. Consider sorting algorithms. Merge sort guarantees O(n) log n time but requires extra space, whereas quicksort has better average case performance at the cost of potential worst-case scenarios. 1. Constant time operations like array indexing remain unaffected by input size O log n. Efficient logarithmic scaling seen in binary search implementations O(n). Linear time algorithms such as basic searching routines O(n) superscript 2. Quadratic time complexities common in nested loops and bubble sort O(2). Exponential growth typical of naive recursive solutions. Theoretical perfection doesn't always translate to real-world success. An algorithm with optimal theoretical bounds might be impractical due to high constant factors or overheads. Engineers must weigh these abstract measurements against tangible constraints like hardware limitations, data distribution patterns, and system architecture requirements. Taming the beast, optimization techniques and their limitations. While Big O gives us a general framework, actual optimization involves many nuanced strategies. One popular technique is memoization, which stores intermediate results to avoid redundant calculations. Dynamic programming builds upon this principle by breaking problems into overlapping subproblems, creating optimized solutions through careful state management. However, this approach often demands significant memory resources. Caching mechanisms act as another crucial tool, leveraging spatial locality principles to reduce access times for frequently used data elements. These optimizations work best when combined with domain-specific knowledge about data characteristics and expected query patterns. For example, in database systems, index structures like B-trees optimize lookup operations at the expense of increased storage requirements and insertion costs. Some optimizations introduce new challenges. Pre-computing values might increase pre-processing time, while aggressive caching could lead to stale data issues. There's also the trade-off between pre-computation and runtime flexibility. Pre-processing steps may limit adaptability to changing input conditions. Each optimization strategy creates its own set of compromises, requiring developers to make informed choices based on application context. The hidden costs. Understanding real-world performance factors beyond theoretical analysis. Several practical considerations significantly impact algorithm behavior in production environments. Hardware architectures play a pivotal role in determining actual performance outcomes. Modern processors employ complex pipelines and cache hierarchies that can dramatically affect execution speeds, especially for memory-bound algorithms. Data representation formats influence both time and space efficiency. Using bitsets instead of Boolean arrays can drastically reduce memory footprints. Input sizes matter less than their structure. A sparse matrix algorithm performs poorly on dense inputs despite having good theoretical complexity. System-level factors like I/O operations and context switching add overhead that dwarfs pure computation time in many applications. Concurrency introduces additional layers of complexity, affecting both performance predictability and resource utilization patterns. Real-time systems face stringent deadlines that force different trade-off decisions compared to batch processing applications. Performance bottlenecks rarely exist in isolation. They interact in ways that defy simplistic analysis models. Empirical evaluation, measuring what truly matters theory provides guidance, but empirical testing remains essential for making informed decisions. Profiling tools help identify hotspots where most of the execution time occurs. Benchmarking frameworks allow systematic comparison of different approaches under controlled conditions. It's crucial to test across various dataset sizes and distributions. Microbenchmarks isolate individual components for precise measurement, while end-to-end tests evaluate overall system performance. Profiling helps uncover unexpected behaviors, such as excessive garbage collection pauses in Java-based implementations. A well-designed benchmark includes statistical analysis to account for variability in measurements. Instrumentation techniques enable detailed tracing of function calls and resource consumption patterns. Different platforms exhibit varying performance characteristics due to differences in compilers, libraries, and underlying hardware. It's important to distinguish between algorithmic improvements and infrastructure enhancements during evaluation. Design philosophy: when simplicity outweighs optimality, sometimes the simplest solution proves superior despite suboptimal theoretical complexity. Readable code reduces maintenance costs and enables easier debugging. Simple algorithms are less prone to edge case errors and generally have lower cognitive load for developers working on them. Maintainability becomes increasingly important as software evolves over time. Overly complex algorithms can become liabilities. The KISS principle, keep it simple, stupid, advocates for minimalism in design whenever possible. There's value in prioritizing developer productivity alongside computational efficiency. Occasionally, an O(n) superscript 2 algorithm outperforms an O(n) log n implementation in practice due to smaller constants and simpler control flow. Readability also affects team collaboration and long-term project sustainability. Elegant solutions often emerge from creative problem-solving rather than rigid adherence to theoretical limits. Contextual adaptation: matching algorithms to application needs no single algorithm suits all situations perfectly. Selecting the right approach depends heavily on specific use cases and environmental factors. Batch processing tasks benefit differently from real-time streaming applications, each demanding distinct algorithmic properties. Memory-constrained embedded systems require careful balance between functionality and footprint. Distributed computing environments introduce network latency as a critical consideration factor. Machine learning workloads involve unique challenges related to training time versus inference speed. Web development contexts demand fast response times with predictable performance characteristics. Choosing between deterministic and probabilistic algorithms hinges on reliability requirements and error tolerance levels. The same algorithm can perform vastly differently depending on whether it runs on a smartphone or a supercomputer. Evolving landscapes: trends shaping algorithm design today. The field of algorithm design continues to evolve rapidly, influenced by advances in computer science research and emerging technological paradigms. Quantum computing promises revolutionary changes in certain domains, though widespread adoption remains distant. Parallel processing capabilities now built into consumer-grade hardware open new possibilities for concurrency-aware designs. Neural networks challenge traditional notions of algorithm efficiency with their unconventional execution patterns. Hardware acceleration units like GPUs and TPUs create opportunities for specialized algorithm implementations. Cloud computing infrastructures offer elastic resources that change how we think about computational limits. Emerging standards for energy-efficient computing drive innovation towards low-power algorithms. The rise of functional programming influences algorithm design philosophies with emphasis on immutability and declarative styles. Conclusion: understanding algorithm efficiency requires navigating a complex landscape of trade-offs between competing objectives. There exists no universal formula applicable to all situations. The key insight lies in developing awareness of these trade-offs so that informed decisions can be made based on concrete needs and constraints. By embracing this mindset, developers can build systems that achieve optimal performance without sacrificing maintainability or correctness. Remember, the goal isn't simply to find the fastest algorithm, but to find the one that best meets your specific requirements within the given constraints.